excellent adventure.
Actually, I left out the word here. It said excellent mathematical adventure in the abstract, and that's really what this is more about. We've had other adventures, but anyway, so this is a little light talk, I guess, at the end of the day. Not too much new stuff, but it was fun for me to look at all this stuff. We've 44 years. Doug and I have known each other since about '78, and we co-authored 32 papers and one blue book up there, and that's a lot. And we've done it through all the years. We did roommates in the '80s and 70s, and so we got a lot of history of many papers. And so I thought I would look at some of those papers through the years and try to see if there's some interesting things that we didn't solve then that I could present now. So you could have something to play with over the next week. Some of them have been spoken about already, it turns out. But anyway, so here's a little history. Doug and I, we met in graduate school. There's actually a story there, but I won't go through it now. But we shared an apartment and we were roommates from '78 to '80. And Dan Archdeacon, who many of you may know, was our third roommate. And so we had a very mathematical apartment there and really did a lot of fun stuff. That's, grad school is a blast, right? If you're doing math and having friends that are doing it with you. And we certainly had a really good time back then. Rick was our advisor, and I got my PhD in 1980, and Doug got his master's with Rick and then blasted up to Waterloo and immediately got it with Ron Mullen. He had done a lot of work already and completed it pretty quickly. So this is actually the oldest picture I could find. And I actually got to thank Janet because she found this, Doug. This is, we did a lot of running back then. This was kind of the first running fad, was back in the late '70s or so. And so that's Doug and that's me. And we're running in Columbus near our old apartment. And so I wanted to thank Janet, Doug's wife, for this photo. I didn't have this one in my archives, but well, we're young and in shape, and we were even doing marathons and stuff back then. I don't think we could anymore, but we could still smile, I guess. So what I'm going to do is go through, I think I've found 10, but that was way too many for a 30-minute talk. So I think I have 9 different papers that we've done going chronologically. Yeah, I can fit that in 30 minutes too, huh? So these are going chronologically, and I'm going to show like photos from that era and the problems we were working on. So the first one actually was cool because it was almost our first paper together. And it was actually 4 roommates, because before Doug became our roommate, we had another one named whose name was Tim Tilson, and all 4 of us are co-authors on this paper, and it occurred in JCTA, and it was a pretty big deal for us, that's for sure. And so, well, what's a row complete Latin square? We've seen Latin squares already today. I don't think we've seen row complete yet, but the idea is that every pair occurs exactly once as in adjacent cells in a row. So you can have column complete or you can have complete, but any pair of symbols occurs in adjacent cells in some row somewhere. So anyway, we found some, not many had been known, and we found some small ones. And in particular, the row complete Latin square of order 9, which is the smallest one we found, was found on this. And so I wanted to have a picture of, again, antiques and things. This is an Apple II that Tim, our other roommate, had bought. And the first time ever you could do computer searches at your house, and because we had a personal computer for the very first time. So great specs for it. I thought I'd show 32 kilobytes of memory. What's that? That's like I don't know, a bit, whatever. I guess 1,000 bytes, but anyway. And a CPU. Anyway, it was made from '79. I think he had his in. It was about '79 when Tim bought his before that, and then the Mac was introduced a little bit after this. So it didn't have a graphical screen, but look at the little picture that they showed. That became Wikipedia, right? That photo up there. Can I do that? Yeah, there you go. So that's the Wikipedia thing. This is predates that for sure. But anyway, Tim found this row complete square of order 9 on his computer, but then he kind of bagged grad school, left, and we we upgraded to Doug. And Doug stared at it one day and saw a really cool pattern in it. I mean, it's a computer result. Usually you look for patterns, but you hardly ever find them, you know. But Doug did, and actually it had little 3 cycles sitting in it, and we called it a generating array. Now we would say this got an automorphism group of a certain type. But anyway, we called it that. And in fact, it was pretty useful. We found those other orders using it. And in 98, I guess, 20 years later, Jeff Hyam proved the row complete squares exist for all composite orders. I still find this one of the more intriguing results, because usually we get stuff for primes. And this is, can't do the primes, you can do the composites. And so that's what's with this paper. Again, this was in JCD. And so just the first unsolved problem is, by the way, he used some of our methods to get some of this, and that was nice to see. So the idea is to make row complete squares. Nobody has solved that problem for primes still. So it's been a while, right? It's over 20 years. Okay. Oh, so look at this one, huh? That's him. This picture comes from my honeymoon. On my honeymoon with my wife, and actually with Dan and his wife, all 4 of us went. We went up to Canada. We were in Columbus where we had gotten married, and we came to Waterloo, and actually Doug and I went and talked to Ron Mullen. We showed him some math ideas we had been working on at the time, and I guess I got a picture of Doug at that time. So this was 1980. Look young there, Doug. I don't know. So here's problem number 2. This is on fast algorithms for finding strong starters, and several other papers on strong starters. We were quite interested in these for a while. A strong starter, we've seen starters already today. We've seen strong starters today. I just have a little example there. The idea is you're pairing up all the numbers in Z11 in this case, except for 0. And you have every difference exactly once. So difference 1, difference 2, difference 3, difference 4, difference 5, and plus or minus on those gives you all the differences. So that's what a strong starter is. We found an algorithm that found strong starters very fast. We actually generated them up to 1,000, which was a big deal. And we made them up to, actually, we made them up to 10,000 at the time, but it was the first successful use of hill climbing in all of design theory. And so we're quite proud of that. It actually evolved Doug's triple system hill climbing algorithm. It's essentially the same one. It's more useful because triple systems are cool and we use them for everything, but it's basically the same hill climbing algorithm. And so that was nice. And so talking about strong starters, in '89, Joe Horton conjectured that there's one in every abelian group, except for those 2 that they don't exist, Z3, Z5, Z9, these 4, I guess, that they don't exist in. And so, and it is known to be true in abelian groups, everyone when relatively prime to 6, but not much more, really. Some strong starters are known, but not a ton. But what I kind of was intrigued by is a cool little picture you can draw with strong starters. You just make cyclic group. These are for Zn. You make the cyclic group picture and you connect the edges. You make a 1 factor of the edges that are in the starter. Okay, and that thing cycles around, and that's how you get a 1 factorization. Of course, we've seen this a lot. And this one here of 129 was a very special one for us because this is the one that was important that we constructed at the time in order to solve the room cube spectrum problem completely. This one was essential. And at the time, before our algorithm existed, the largest one was like order 50 that you could get on the computer. And we made this thing in 6 seconds, if I remember right. And I had a friend who had access to a big printer at the time. And he actually put that, and that was in my PhD thesis, was that picture there. And it appeared recently. And that's why I put this up again, because I saw it in a paper not too long ago, and it made me think that stuff's going on here. So a starter is a Skolem starter when you look at the differences, you don't use the mod part. So difference 3 will actually look like a difference 3. You'll never use the modular arithmetic. And so those are called Skolem starters, and you make Skolem sequences with them because that difference is going to be how far the symbols are, across from each other. And Shalaby conjectured that basically these things exist for all orders, but not a lot is known. He made some small ones. There's a product construction and a few other cases. But they had this picture in their paper. It's recent. It's 2018, and I just thought it looked pretty. And they also had my picture, so that's why I didn't mention it today. But the deal is, without that using the mod thing, you're never crossing the infinity zero line, right? And so that, because you're never using the mod for your difference. So that makes a pretty picture. Actually, they constructed this out of some cosets and stuff, so it's even prettier than just having the Skolem property. So anyway, you can see I have about 3 or 4 slides, I think, on each of these topics. I'm just kind of blasting through some greatest hits. But so the first one, the problems that relate to this idea of starter. Oops, backwards. Is Horton's conjecture for all abelian groups and Chalabi's conjecture for the cyclic. He only conjectured that for cyclic groups. I don't know what Skolem would look like in other groups, but presumably, yeah, I don't know what that would look like. Anyway, so 2 problems to work on. You can start doodling right now, maybe prove it by tonight. I don't know. So again, we're working through time. This is 1983. Some of the greatest conferences I went to were the Maniwat conference. That's Manitoba and Waterloo. The combinatorics people there at both schools got together and had this old convent, which is a nice way of saying it. It was a kind of a dumpy old place in St. Pierre, Manitoba, in the middle of nowhere. But maybe you'll recognize, let's see, whoops, wrong button. Let's see, some people. So where's Doug? Okay, there's Doug. There's me. There's Ralph Stanton. There's Ron Mullen. There's Scott Van Stone and John Van Rees and Evie Nemeth and Paul Schellenberg. So this is like people from Waterloo, and Bill Coquet's there too, right? Yeah, there he is, Bill. The rest were grad students. They kind of served us food and brought us beer and things. It was quite a conference. Really enjoyed it. So that's 1983. And then Doug and Janet came to Burlington in 84 and made Doug climb mountains and stuff. So that's us on top of Mount Mansfield, the tallest mountain in Vermont. And actually, they weren't quite married at that time, but got married soon after. I got a beard. You're looking good, man. That's after the hike. So let's back that up. That was good. So that's at the top still. Next paper, we're looking at room cubes now. Room cubes, this is 80, we're up to 81. Wow, we're not moving very fast. Better move faster. Orthogonal 1 factorizations, you got 2 1 factorizations, got a bunch of 1 factors in them, and you put them together, and any, no 2 edges are together in both of the 2 1 factorizations. How do I say it better there? They have most 1 edge in common. And so what's the maximum number of mutually orthogonal 1 factorizations of Kn plus 1? That's a fundamental kind of question that I've really been kind of my favorite question forever. And we call this number nu of n, just like n of n for Latin squares. For orthogonal Latin squares, this is nu of n, and there's some results there. And in particular, this is one I'd like people to really take a look at, is that we can show that n of n is at least 5 for everything. Doug and I proved 3 for everything bigger than 9, I guess. And but 5 is true for everything bigger than or equal to 9, except for 17, which we can't solve. So that's still an unsolved problem there. And then there's a prime power construction. So there's the table. This is in the hand. By the way, most of these things that are like white there, I grabbed it from either the handbook or maybe the original paper or something. But this is a handbook one, I believe. So here you can see they're all 5s. The primes are cool. They got bigger numbers because you got nice constructions there. But you can see 15 here is that's the one I was talking about. I said 17 because it said 17, but it's really the complete graph on 16. We want to find 5 orthogonal 1 factorizations of that. So the problem is to improve these bounds. And there's an upper bound conjecture. This is one of the few examples where the upper bound is not a nice, kind of a nice construct, a nice object, and kind of obvious that this is the most you can do. So the upper bound is you can do roughly half. Grossman and Wallace had that conjecture in 73, and that's been, obviously it's still a conjecture and it hasn't been disproven or anything like that. So that's a great problem, really good problem. We've all looked at that quite a bit, I believe. But some people actually think it's wrong. In particular, Luke Tierlink does, and Alan Ling believes it's wrong. Give him a little credit here. So they think it's n-1. They think it's twice as big. And so that would be a nice thing to look at. So I wanted to have something new here. So I have one little new thing. We want to talk about orthogonal starters. We've seen starters. They're orthogonal if they have a nice property with each other. In particular, the differences of the pairs are all different. So to get from 2, 3 to 3, 4, you got to add 1. To get from 4, 6 to 6, 1, you got to add 2. And from 1, 5 to 5, 2, you got to add 4. As long as those are all different, you're orthogonal starters. And then from those, you can get orthogonal 1 factorizations and room squares and higher dimensional room thingies. So I want to get as many of these as I can, orthogonal starters, to beat those records that were on that last slide. And so these are new results from about 2000 when Alan and I found them. We didn't quite think one isolated one was quite worth publishing, but I'll probably put it in the new result page of the handbook. So we found that nu of 21 is at least 6. There are 6 orthogonal starters. So that finishes that. And nu of 33 is at least 7, because there are 3 orthogonal starters, but they're orthogonal strong starters. So you get them, you get their negatives, and you get the pattern starters, the S, S1, S2, S, and the minuses. And that's going to give you 7. So those are world's records. So here's the old table and 2 new results in there, which is cool. So the 21 went from 5 to 6, and the 33 33 went from 5 to 7. So that's something. And so the problems here in this area of orthogonal 1 factorizations, orthogonal starters, would be to find some new bounds, new lower bounds on nu of n, get that nu of 15 guy to be at least 5. It almost surely is, I'd say, and then mess with that upper bound conjecture. See if you can hit more upper bounds or beat the purported conjecture of Grossman-Wallace. Well, now we're in 87. That's the Vermont workshop that I ran for, I don't know, 5 more than that years. Let's see, there's Dan in the front row, Spiros, Don is there. There's me, where's Doug? Doug, you're in the back row next to Alex. Kurt was there. And Doug kindly actually gave a couple of really good talks there. We were in the little conference room in the math building. And there's Doug at the, remember what those things are, right? The slide guys. he's giving his talk. And then we had this great conference up at the IMA up in Minneapolis. So you know who Doug's with there? You know, Luke Tierlink. So that's Luke. And so he was there that week. That was a fun conference. And I just thought that was a good picture of you too. Okay, okay, we're moving along. Perfect 1 factorizations. Where have we seen those before? Well, not much to say here because Ian just said it all. Kotzig's conjecture. We got some new ones. It was one of your little lines there and all the stuff that's done. But we did have a neat top. These n quotient coset starters are very useful things, and we were happy to come up with that. It made it very quick to check if a starter gives you a perfect 1 factorization. If you're looking in K 3,126, you only had to check like 8 pairs together, as opposed to 3,126 choose 2 pairs, and that's a better improvement. That's how we got the results. And all the results, everything, I got you here, Ian. Again, here everything is on his page. At least it was at one point. And so these are the following the examples that are known, and more even, I guess. I like some of the little ones. The one Adam Wolf came up not too long ago was cool, and David did a similar thing and came up with another new one there. So those are kind of cool, using doubling kind of constructions. So the problems here obviously are to find new orders or to prove the conjecture, and it probably happens soon. Ian will do it. So now we're in the 90s. Hey, we're up to the 90s. This is Vermont Stubborn Workshop. Now we're at Stowe. They got a little bigger. The conferences did. You can see your favorite people there. There's Esther now, and Spiros, and lots of people in there. And I can show you these photos later if you're interested in seeing what people look like, I don't know, 30 years ago now. And that's Ernie Brickell. He went to grad student school with us also at Ohio State. So we were old buddies with him. And so I got everybody to climb the mountains. That's the mountain right next to Mount Mansfield. So let's see, there's me and there's Doug. He climbed, and Luke again, and Chris, Roger. Don, is that you? Yeah, I think you are, yeah. And then actually we had everybody over at our house. So that's me and Dan and Doug and Ernie and all our kids at the time, who are now way grown up. I know mine, the second one over is my son. He's 40 years old. So, yeah, well. And then another workshop. This one, they got bigger, and look at all the great people that were there. And it was really quite a good thing that we did. There's Doug again, and maybe I made sure you're always in the first row. Although in the first one you were in the last row. So, and Bill Martin is there. Is he here yet? No, no, didn't make it yet. And there's Alex, because he's always tall. And there's the Charlie, the old Charlie look, the bearded guy. And okay, anyway, again, we can look at these. I think it's fun. And we did the Blue Book in '92. So now we're talking about frames. This is a paper from '93 and another one in '94 that we did with Julie on finding some frames, a certain spectrum of certain classes of frames. So this is a frame. We've already seen some today, a really great, a room frame. Now they've been generalized to all kinds of objects, but a room frame essentially is a room square with holes in it. So in the holes are supposed to be these symbols that you kind of pretend are together as pairs, but you don't have to draw them in, because you can't, in fact, if it's like a 3x3 thing there and so on. So anyway, a frame of type 1 to the 1, 3 to the 4, it's going to have one hole of type 1, 4 holes of type 3, and in every row and every column, all the symbols occur except for the ones that are thought to be in the hole, and every pair occurs exactly once except for the pairs that are thought to be together in the holes. And so these are room frame. Oh, and in fact, on our cool mugs is a room frame of type, oh, there's Bill. It's type 2 to the 6. So beautiful, beautiful mugs. Make sure you get one. So there's this, again, a handbook kind of thing. These are uniform room frames. They basically exist. That means that all the holes are the same size. And then there's ones with 2 hole sizes. And that's kind of sparse there. You can see 2 to the A, 4 to the B. That means holes are size 2s and 4s. You get all combinations of 2s and 4s, but what about 2s, 4s, and 6s or something? There's a lot of things that are missing there. And then the bottom one is these room frames of a certain type, a bunch of 1s and one big T. So a lot of 1s, and that's just a room square with a subsquare, it turns out. And you can see here that there's some exceptions. In fact, this is except when U is 4 and T is 14, and it's except when U is 19 and T. So just one exception here for each of those. But in the paper with Zuli, recently, sorry, that was the paper that with Zuli, we had those 3 exceptions. But recently in 2010, we got rid of all those exceptions. So take your handbook and cross those out, because they're not exceptions anymore. They've all been shown, all 3 of them. Yeah, so where are you going to work on that? Anything you want, right? 2 holes, 3 holes, or 2 holes not of those sides. There's a lot of stuff there, and there's a lot of techniques that are known, that's for sure. And so I think a lot of progress could be made now with more modern stuff. And what about skew? And I'm not really sure. I think just the uniform. Doug did at 1.2 to the end skews, but I didn't really look it up. So you can mess with those. 95, we're now in Fort Collins. This is the Bose Conference, RC Bose Conference. We're on top of Trail Ridge Road there, so we're also up on a mountain, sort of. And that is Doug and our old roommate Tim and me and a Korean mathematician, Hong Song. And this is the strangest one I found. Not that Don isn't always strange, but this was my daughter's bat mitzvah, and I don't know why these guys were in town, but they were. Anyway, so we're all dressed up, huh? And there, 98. And then in 99, Rolf Rees sort of had a conference out in Newfoundland, and so we all went out there. This is the easternmost point of North America. And so we took pictures there, one's with Bill and one's with Frank Bennett and Rolf. Okay, all right. This is, I like this one too. I guess I like them all. This is O2, and we're looking at bicoloring Steiner triple systems. So what you want to do is make sure your triple system is colored, and every single block, it has exactly 2 colors in it. So 2 of one color and 1 of a third. No rainbow ones. You don't want any with 3 colors in it. A lot of work's been done on this, a lot of stuff. And I just kind of want, that's the definition, I just kind of wanted to talk about one little ingredient that we found to make these things, because that was kind of, I thought, well, it was an interesting part. So Charlie and Alex and I had done something that needed these same kind of things. They were called ABC forbidden Latin squares. And let's see, I got a picture of it. So you just partition up the symbols and the rows and the columns into sets A, B, and C. And that's kind of what you want. In the A by A cell in the beginning, you don't want any of the C symbols. And in the A by B, AB cell, you don't want any of the B symbols. So that's what you want to make. You want to just try to make a Latin square that has this property. Then you could make bicolored. Oh, actually, you had a multiplication theorem. This gave us the multiplication theorem to make bicoloreds from smaller bicoloreds. And so I think I missed a slide. Yeah, I did. Oh, no, I'm going forward. Damn it. Okay, so that's that. Anyway, so we generalized this for our paper because we wanted to get a singular direct product instead of just a product. And so really you have ABC, that indexes the rows and columns, and you have X, Y, and Z partitioning the symbols. And that again describes it. And so instead of trying to read that from the paper, here's an example: 5, 5, 2, 5 rows and columns, then 5 more, then 2, and then X, Y, and Z. X has 6 symbols, 1 through 6. Y has just X, and Z has A, B, C, and E. A, B, C, D, and E. And you can see that, I think if I remember right, the first one said no X, right? And so if you check that, there's no of the X's. There's no in the first little square. Anyway, this is one of those. They're not hard to really understand. We found for the ABC one, we found a necessary and sufficient conditions. The original paper with Charlie and Alex. And so it was if ABC is less than, the max of that's less than n over 2. And that gave us our product constructions. And so, but in the paper with Doug, we found necessary conditions for the existence of those ABC, XYZ, FLSs, forbidden Latin squares. And that's them. But we could not, and so again, this gives us our product construction of V into a 3V minus 1 plus 1. And so the question here really in my mind is, what are those necessary conditions sufficient also? It's pretty simple to state, not too easy to do, I don't think. And then on the bicoloring, there's just tons of problems there, just tons of them. So I didn't want to get into that. So now we're in the 2000s. There's Doug in my office and us in Corfu. And got a minute? So anyway, I don't think this is a great question. I won't go through any of the details, but you know, when you superimpose Latin squares, you say how many pairs of symbols do we get? And if they're orthogonal, you get n squared of them. Well, what if you have? Let's just skip to this. There. So what if you have 50 squares of all 3 by 3? What's the most number of superimposition of pairs you could get when you superimpose all those guys on top of each other? You know, pairwise. So if 2 are orthogonal, you get 9, and then another guy won't be orthogonal to both of those, will they? So maybe it's the same. So it only adds 3 pairs from the first and 9 from the second. And you say, how many pairs? What's the total number of pairs we can get? What's the most? And we found a bound. That's one of Doug's really great things he does. He's really good at finding bounds. So anyway, we got a bound on it. The naive one is S choose 2 m squared, right? You think, oh, if they're all orthogonal, you get S choose 2 m squared. But of course, they won't be when you get 50 of order 3. So anyway, here's the upper bound that we proved. And we found that, so there's an example of 4 by 4 Latin squares. No, 5 by 5 Latin squares, and you want to get 14 of them. Okay, it turns out you take the 4 orthogonal guys and you take 3 copies of them, and then you take any 2 of the other 2 again. That's the most you can do. That's the best you can do. And it hits that bound. Do all the solutions look like this? I think so. We conjectured they do. We conjectured that if you're going to hit our bound, then you must have contained m-1 moles of order m. You pretty much have to have those somewhere in your whole set. And then a further conjecture says they're balanced. You take, it's the same number of each of them, but then you go up or down on the remainder. And the weird thing is that these conjectures are the same. We proved that one implied the other. And we verified them for 3, 4, and 5. And we'd love to see, I'd still like, this is a cool problem, a proof of something like this for the prime order. And then we don't know squat really about non-primes when you don't have a bunch of orthogonal guys to mess with. We did m equals 6, and we found 3 squares of order 6 got at least 91 pairs. 5 of order 6 got 295, but that was kind of just fiddling around. I think it could be more systematically studied. Just go to the pictures now. So we ski. This is Mad River. That's the ski area that I'm a partial owner of because it's the only cooperatively owned ski area in America, and I have a share on it. And that's us in Victoria, where there was a conference that we got to. Bouchard Gardens, is that it? Yeah. And then this is Rick Wilson's conference that we had at Caltech. So there's me and Doug and Peter is there. And all right, I'm done. So I do love this one. So this is one I was telling Esther about a little bit. This is a frame, a 2 to the 5th frame that has a whole bunch of transversals. And if you take those transversals and you project them row and column down, you can make a really cool tournament, right, on 10 players here. And you have weeks and sites. Obviously, everybody plays everybody else, except for the 2 that are in the hole together from the frame. And when you take it down, you can also call it, because of the transversals, you can have time of day. So everybody plays in time of day, the same number of times, and everybody you can also have referees, right? And everybody has a referee. The referee sees everybody the same amount of times. And so you can actually think of this as raising this up in a 3-dimensional way. And so it's a 10 by 10 by 4 box. Think of the color as each height. And then again, looking at these projections, you get these things. And these are almost balanced tournament designs, except that they're missing the pairs that would be in the holes together. And so really it's a spouse avoiding tournament, 10 players over 10 weeks at 10 sites, 4 times a day, 4 referees. Each person sits out 2 weeks. So that's the pair, maybe their spouse, right? And they're on family vacation for the 2 weeks. And it's very, very balanced. So that was a hoot kind of to make this, and at least wanted to show it. And so the problems here are, the original question we had was do this with the room square. But now I think maybe you can do something with frames instead. And so we went to Mykolaiv in Czech Republic. There's Charlie in that one, and Marco. We're drinking wine. There's a really cool castle we were in, had a wine cellar with a big thing of wine. That's a big vat of wine behind us, although it wasn't very good. And now from there, we went up to the British conference. That's Drygate was a brewery. And this is Charlie's, should I give away your riddle? Yeah, well, so this is Charlie's conference in 2018 in Singapore and Vermont, because I couldn't get there because of technicalities with things called a passport. Anyway, it's a long story, but I'm the different one. But okay, so that's I didn't think I'd get to this one. Do I have any more pictures? There. So we were in Boca a couple of years ago. One last picture there, and so thank you for your